Hey guys, it's JM. Today we're going to talk about Chia Farming power consumption. There are some easy ways to basically estimate the power that a farm is going to consume, and you can look at ways to kind of measure it and see how efficient you are, especially versus other farmers. At the end of the day, farming is a competitive thing, and you're going to want to be able to know how to get the lowest TCO and how to have the most efficient farm possible. So the good thing about Chia is you can have a good TCO even with small farms. Actually, the smaller the farmer, you can actually get really good power efficiency because often if you have just a single external drive or these really power efficient NASs that just consume a small amount of overhead and then are made to house a bunch of drives, you can get very good power efficiency. Obviously, you have to weigh those things with the cost, right? So NASs, although they have really great power consumption, they tend to be a little bit more expensive per bay than, say, building your own desktop or doing a DIY solution. Now you can get some efficiency at scale from doing mid-size or like rack scale stuff, but generally it's actually less efficient in Chia to do these because you have more overhead from stuff. Like in a rack scale environment, you need to have extra cooling to basically cool the data center that you have the rack in. In a mid-size farm, generally some of these older equipment that have good costs for Chia farming tend to not be as power efficient as new equipment. So when you think about this, what hardware is required, people are generally acquiring JBODs because JBODs are just a bunch of disks, and that's the best place to put a lot of hard drives. And this is what enterprises are designing to have high capacity in low amount of space. As far as terabytes per rack unit, it's very dense storage. In Chia, you want to use the highest capacity hard drives generally you can find. Now I'll show you some examples where even mid-range to high capacity, ones that were high capacity, say 3 to 4 years ago, are still very competitive because they can be found much cheaper than the new drives. But drives that are like, say, 10 years old, like 3 and 4 terabyte drives, are just not going to be competitive for Chia farming. Now you want to use, basically, there's not one way to do it, right? I mentioned you can do NAS, desktop, DIY, JBOD. I'm going to give you guys a couple examples of ones that I'm most familiar with. Ones that I'm running are kind of rack scale stuff, and then kind of like a standard desktop application. But the most important thing, right, if you're doing farming correctly, the majority of power is going to be consumed by the hard drives themselves. And that's where we're going to spend most of the time today talking about how do we determine how much power hard drives consume. Now you could go individually measure the 5 volt and 12 volt rails on each hard drive during farming, but I have a little easier way to do that. We actually can calculate the, basically Seagate and WD measure these for us on their spec sheet. And so they're going to make our lives quite a bit easier than having to go measure this on each drive, and we'll show you how to calculate that. So before we go there, I'm going to talk about how farming works. So in farming, the farmer is going to receive a challenge that comes from the VDF, or the Time Lord is going to send the verifiable delay function. And the farmer is going to send these signage points to all the harvesters, and the harvesters are going to go through this thing called the plot filter. And so the whole idea of the plot filter is to reduce the amount of I/O to the drive. And in Chia, the constant is set to 512. So you're basically reducing the I/O by a factor of 512. So when that challenge comes in, you calculate this plot filter bits in SHA-256 of the plot ID, which is a random generated for each plot, and then the challenge hash and the signage point. So each signage point and challenge, you're going to have a different you're going to have a different plot filter. And then, so the way this works out, the filter is set to 512 in such that when you calculate this plot filter, there will be a bunch of zeros on the hash. And if that plot has a certain amount of zeros, it can pass the filter, and it can be eligible for this next phase, which is the proof quality check. And so when the plots pass the filter, they go to this proof quality check, which is not a full proof of space. You just need to do a few reads to see if you have any matches. And if the proof quality check meets the required iterations, and this is kind of gathered from the difficulty and other things, then the proof of space is good. And then you can go fetch the entire proof of space and send that back to the network. And that's how you create a full proof of space. Now in a pool, you basically do this the same kind of way, but they basically have these things called partials. And a partial is really just a full proof of space. And you go through the same process, but with a different difficulty. And so you're basically sending them, instead of, for instance, if you have a couple 100 terabyte farm, you might be waiting a couple months before you actually find a real proof. And in a pool, they can basically set the number of partials per day to a certain target. Like in the reference code, they set it to 300 per day per target. And so you basically can know on average for your farm how many proofs of space you have to send per day, but this is so the pool can verify that the farmer is indeed actually storing as much data that they say they are. And they use that difficulty and the difficulty that they set and the number of parcels per day to kind of determine how much farming capacity these farmers have. And this is the same calculation we use for the net space, and so the farmer has to submit these good parcels back to the network. So what happens with this drive utilization is the actual amount of IOs the drive has to do. One is obviously determined by how many IOs are required to do a proof quality check and a full proof of space. So a proof quality check is between 7 and 9 reads, and now the amount of data is right around 8 kilobytes, but it's just slightly over. And so generally these reads happen to be 12 or 16 kilobytes because of the sector size and alignment of the drives and file systems. And then a full proof of space is 64 random reads. And you have to do you have to go walk through all the tables and then create this full proof of space. And so the actual IO per disk actually depends on the number of plots per drive, which is generally determined by the K value. And so if you have a K equals 32, you can kind of see over here how many plots per disk you can fit and what the actual average bandwidth per drive will be. And if you basically, as the drive gets bigger, you can fit more plots on there with the ISO K value, then you can basically assume that more plots are going to pass the filter because you're going to have more chances for the filter because you have more plots generating more IO in the drive. Now, the worst case is difficulty 1 in a pool where each plot is basically doing about 10 partials per day for K equals 32 at difficulty 1. So difficulty 1 is kind of your worst case scenario. And the good thing is that in your worst case scenario, of course, difficulty 1, as you can see, is about 4 to 5 times higher than what you would see as K equals 32 on a standard pooling farm. But the worst case is actually not that bad. Even in the worst case on an 18 terabyte drive, it's about 20 kilobytes a second. So that is far less. It's hundreds of times less than a enterprise workload. So an enterprise workload is generally rated at 550 terabytes per year. This is only reading a couple hundred gigabytes per year. And so once you're doing farming, it's a read-only workload. It's reading a very small amount of data. So this is when we say that farming is very light workload for drives, this is what we mean. So I have a snapshot of my Grafana from my personal farm, which I have kind of a collection of different size drives, mostly 16 and 18 terabyte drives. I've kind of just taken a random snapshot to show you that indeed are hypothetical values that if you go to the docs.chia.net, we have the storage farming workload analysis document that basically goes through the calculations that we use for the number of plots per day, the filter passes, number of IO, and we can calculate, with the number of K value and the number of plots per drive, what the IO should look like on a drive. And it ends up, when we measure this data in real life, it ends up being real close to what we had forecasted. You can see here, this is basically a summary of that Grafana data, which is in my farm. I have 300 something drives and you can see how many end plots of K equals 32 fits on each drive. I have running only K equals 32 in my farm. I have mostly 16 terabytes and 18 terabytes, and you can see as the drive capacity gets bigger, the amount of kilobytes per second gets bigger. On an 8 terabyte drive, it's around 6.6 KIB per second read. On an 18 terabytes, about 15 and this is what I'm measuring in the real world. Which is slightly higher than what we had forecasted. So there's a little bit overhead in the file system and some other stuff that's kind of hard to model. But this is insanely low amount of IO. This is like nothing, right? A single hard drive can do like about 280 megabytes a second read, all the way down on the outside platter. On the slowest on the drive, it can be about 130 megabytes per second. So this is a very, very tiny amount of data. And again, a hard drive can do a couple hundred IOPS. This is less than 1 IOP for the Chia farming workload. So why is this important? This is important because when the plots pass the filter, so every signage point's around 9.3 seconds, and then the harvester is scanning all the plot files on the hard drives, and basically for ones that pass the filter, you're doing these proof quality checks, and eventually for the number of partials you have per day, when the pool sends out the partial request, you have to basically do a full proof of space in this partial and send it back to the pool. So in this time, the drive is sitting mostly idle. It's actually idle 99.7% of the time. So the drive, when you're doing farming, this is with hundreds of drives on a single harvester, as you just saw, but it doesn't really affect the amount of I/O done to the drives. The drives are basically just sitting there mostly idle. And the probability that it's going to get accessed per minute, you can basically take the cumulative distribution function or binomial distribution and basically just say, okay, if you have, in a minute, you can say how many signage points are going to be in a minute and what's the probability of at least one plot passing the filter. Because if one plot passes the filter, then you have to basically do some I/O. And you can see on an 18 terabyte drive here, or a 16 terabyte drive, it's above 80%. So there's a pretty good chance that the drive is going to be accessed every minute or so, at least once. Now, again, you can see here, even on a 20 terabyte drive, there's a 10% chance that a minute goes by that the drive doesn't get hit with any I/O. But for the most part, the drive is not doing anything most of the time, but then it does a little bit of data for these proof quality checks and then stops. So what happens during this time? So hard drives, modern hard drives, there's all kinds of different power stuff, and SATA and SAS have different kind of methods, but at least now hard drives have kind of consolidated on this modern power saving feature called EPC, or extended power conditions. And basically the way the hard drives save power, and in the future we'll talk about SSDs and how this is really exciting for SSDs, but today we're talking about hard drives because hard drives are used in Chia Farming predominantly, of course. So in hard drives, they basically save power based on how idle the drive is. So these are based on a timer setting. So this is right from the Seagate spec. This idle A says reduced electronics, and this is disabling some of the servo systems, reduced processor and channel power consumption, the disk rotating at full speed. And idle B is where the heads are unloaded. The disks are spinning at full RPM, and the actuators park the heads, and you save, looks like about 2 watts, right? It goes from 5.28 watts to 3.49 watts. So you're disabling most of the servo system, and you're also unloading the heads to the ramp. And this is called idle B. Now, idle C is when your heads are unloaded and your disks are spinning at reduced RPM, and they can't go all the way down because you need to spin it right back up. So it doesn't go down to like a very slow RPM. You can see you just have a kind of modest power saving here. And standby Z is where the motor's spun down, heads are unloaded, and the drive still responds to non-media access commands. So when it gets a command, it can spin back up, and that spin up time takes about 10 seconds. I've taken similar specifications from the Western Digital HC550 specification. You can see it works exactly the same way. Idle A is where the servo is disabled, but the heads are loaded and the spindle's rotating at full speed, while idle B is where the heads are parked. Now, in idle C, again, the heads are loaded, but you're spinning at about 85% of the rated speed. So now we've learned that hard drives save power. Now, you can manually make the drives go into these different idle states by sending a command. Or what is the most common thing is that these have timers on them. So say, for instance, the idle A timer is 10 seconds or 20 seconds. If the drive is not doing any I/O for 10 seconds, then it will go into this idle A system, where the servo is mostly off. Idle B, these timers are generally set to 120 seconds or 600 seconds, and I'll show you some different examples of some models from different vendors and how to check that. But this is when I mentioned in Chia where there is some times where you go about a minute without any I/O, even on a big drive, just the way the probability of the plot filter works. So every once in a while on the default settings on a Seagate drive, it may drop into idle B. Now, if you were really savvy, you could try to set the idle B timer to basically aggressively go into idle B and save a lot of power, to try to spend more time in this 3.6 watt state versus the 5.6 watt state. And I'll explain a little bit why that may not be the best idea. So if you just look at the power consumption per drive, the way we measure power efficiency on a drive is called watts per terabyte. So if you look at the power consumption of those drives, it isn't the same per capacity. So some smaller capacities have different number of actual physical platters on the drive, and they consume slightly less power. They still have the actuator, they still have the motor, so it's mostly very similar power. But you can see, from a little over 5.3 watts on an 18 terabyte drive to a little over 4 watts on a 10 terabyte drive, there is a little bit of a difference on the capacity of the drive. But if you look at the watt per terabyte, you are going to get the lowest watt per terabyte, which is the most efficient on the highest capacity highest capacity disk drive. So you're always going to be most power efficient when you're buying these high capacity drives. But you can see even these range of 12 terabyte, 14 terabyte to 18 terabyte is pretty competitive. And 10 terabytes where you start getting into that older zone. And when you look at 4 and 8 terabytes, okay, now you have to, when we talk about total cost of ownership in a bit, that's where you have to get those drives for a very low cost to make them competitive with farming on higher capacity drives, because you're spending more money on the energy consumption for the power on these drives. And you can see, so again, in farming, again, we spend that whole idea of going through that process of finding out how much idle time the drive has is because if the drive is idle 99.7% of the time, but it's being accessed every, on average 80 to 90% every minute, then by the normal idle timers, you're actually going to spend the majority of time in idle A, which is you're going to spend 99% of the time in idle A, and about 1% of the time you're going to spend doing these random reads, which is peak random read would be 9.45 watts, but we just mentioned, in Chia you're only doing about less than 1 IOP. So this is not a tremendously high power workload. So the idle A is actually a pretty good approximate for the power consumption in Chia farming. It's going to be almost spot on to what the idle A power is measured. Now for idle B, this is really interesting. So we have this cool workload. You have farming is 99.7% idle, but the drive's being accessed pretty frequently because of the signage points. So the idea is, could we set the idle B timer really aggressively low so the drive goes into idle B right away after it does an I/O, instead of having to wait a long time to basically have to wait a long time before it spins back up. Now this is interesting because you can save about 2 watts, but the thing is that this load unload cycle is not a free lunch. The hard drives, the reliability specs, they actually rate this to about 600,000 cycles. And this is pretty common on enterprise drives between Seagate and Western Digital. It's both 600,000. So this load unload cycle, every time you do a load and unload, you basically put a little tiny bit of mechanical wear on that head loading. And then, if you do it too many times, there's a small chance that some particles can get in the drive. And that's where you get things like reallocated sectors, when the right head bumps into one of those particles. So, now we're at a tricky trade-off, right? Which is we have a way to save power, but there's a trade-off between power and reliability. And of course, this requires changing the default timer values. So this is a pretty tricky situation. Now, Western Digital has done a deep study on this, looking at everything from changing the times of the signage points, from looking at changing the plot filter to number of K n values, n number of plots per drive, which is the number of plots per drive determined by the K value. So you can see this n of P equals 165. You saw that was basically the K equals 32 for an 18 terabyte drive. N equals 80 is a K equals 33. N equals P. This orange one is 40 is K equals 34, 35, 36, 37. Okay, so you can see as we get higher K value, even on the K equals 33, if you basically are doing, it says percentage of load unload rating cycles consumed per year over the 5 years. So if you were to set the idle timer on the default, or basically setting it so they're going to spend a lot of time in idle B, you can see this 3.6 watt means you have a very aggressive idle B timer that the drive will be spending majority of time with the heads unloaded rather than loaded. Unfortunately, you'd use up 80% of the rated life cycles per year. So that makes that not good, because then you want these drives to last for 5 years at least, but much longer generally. So even K equals 34, which is this orange line, is about 40-something% per year. And so now you start getting to the point where if you really want to get tricky with this, you have to have K equals 35, K equals 36, and even higher, to where it even makes sense to have an aggressive idle timer. And because if you're going to save the power, you're not going to do all this work to get halfway there. You're going to want to go all the way down to the lowest power. And then on the timer settings, you can see here, if you have a very aggressive timer, then you can see the average power consumption that on a very small timer, you can basically get any of these K values to go into a majority of time in idle B. But this is where it gets really dangerous because you're actually using up a lot of your load unload cycles, and this is not a good thing for extra mechanical wear and tear in the drive. So basically, the recommendation today is just to have the drive sit in idle A, or just disable the idle B timer. If you're using K equals 32, you should absolutely disable the idle B timer if possible, or set that timer value somewhat high. And the way that you can do that is, Seagate has a tool called SeaChest PowerControl, which is you can manage your EPC settings. And you can show your EPC settings to basically show what timers are on the drive. You can see here I have a Exos X18, I believe this is a 16 terabyte or something like that. And it's showing the idle A timers once, one, and it says all times are in 100 milliseconds. So these drives go into idle A like almost immediately after an IO. And then idle B, where this is 1200, 100 milliseconds. So it's basically 120 seconds. Basically, it's 1200 times 100 millis, and then in milliseconds. So you're basically have 120 seconds is kind of what you're looking at for the idle timer. And I mentioned that, hey, wow, there's some times where every once in a while with this 1200 second, over the course of a year, I've got a handful of load unload cycles just with the idle timer default. So ideally, you'd kind of want to, on a Seagate drive, kind of want to turn this off or set that timer higher. If you have the default settings, it's really nothing to be concerned about because you're just doing a few a year, and this is you're completely well within the range. On an enterprise drive, I don't know how reliable using the Seagate tool is on a WD drive, but you can in fact run this on a WD drive and it works. It gives you the timers. So it shows you the timer of 6,000, which is 600 seconds, so 10 minutes. And with an idle B timer of 10 minutes, the drive will never go into idle B in Chia Farming because there's a 0% chance basically that you'll never have a plot pass the filter with that long a time. So this is a pretty cool tool, and you can get it off Seagate's website. They also have a repo for Open SeaChest where you can download it off their open source page if you would like to do that instead of downloading from their page. But you can set the idle B. You can set it enable, disable, default, or timer value, or set a timer value. So you can set the idle B timer to whatever you want in milliseconds. The power measurement tool, I've never actually found a drive that has a firmware that enables this, so it might be something that they use for testing. And then power balance feature. These are just some of these things where you can enable the different EPC modes. But yeah, the one you're going to want to do is really just these two commands, which is show EPC settings, which shows you the timers, and then you can do idle B disable if you like. Now in SATA, there's other kinds of DIPM is device initiated power management and all this stuff. There's all kinds of other power stuff in SATA that's really meant for laptops and mobile devices. And APM is the power stuff that used to be the dominant power profiling for hard drives. You could basically set these automated power levels, and you could set the value higher or lower. But again, most modern drives have eschewed that in favor of EPC. So now, okay, so now that we know how to look at the power consumption of a drive, what do you care about in Chia Farming? Well, okay, in Chia Farming, the ultimate goal is to have the lowest total cost of ownership. And the way you get there, obviously, is you want high storage density because you want a large number of drives per rack unit. You want to use large capacity drives because having the largest density will have the least amount of cost on supporting infrastructure like JBODs and rack space and power and cooling and all that stuff. But you want to minimize your capex. You want to buy used or recertified or renewed drives if possible. You want to use as much underutilized storage as you can. So basically, you want to have, and the TCO. Remember that the metric is the TCO. That's the balance of all these things. And you'll see when we look at a few examples that there are a few ways to competitively farm Chia. There's not one solution. And when you look at minimizing capex, again, it's just dollar per terabyte. Get the cheapest dollar per terabyte. You want to minimize power consumption of supporting infrastructure. So you want your farmer and harvester and your JBOD and all this stuff to not consume more power than it needs to, because the only thing you make money on in Chia is the amount of storage capacity you're putting to the network. So everything else is utterly irrelevant. It's really just a supporting infrastructure to be there. So in a very well and power efficient farm, you want the majority of power coming from the drives themselves. And you want to keep the drives cool enough to not impact reliability. So you don't want to, have the drives running too hot, which, above anything above 50 C is kind of like worrisome. You really ideally want them, below 40, and if possible, even between 30 and 40. So, but again, the drive manufacturer will just say, hey, the mean time between failure and reliability were measured at these certain temperatures. So I get that question a lot, which is what is the right temperature? And the answer that I get from the hard drive vendors themselves are basically, hey, we specify a temperature rating that we measure our reliability against. So that's anything below that is good. But of course, hard drives have moving parts, and the cooler you keep them, the more reliable they'll be. And of course, nice to haves. These are not part of TCO, but they're nice, of course. Quality of life things. A lot of people can't do farming if it's too loud. You want hot swap to be able to replace drives if a drive has failed. You want enclosure management to basically be able to understand what slots the drives are in, so that when you do have a drive failure, you can identify those drives easily, do a locate on them, find the drive, remove it, replace it. Again, these are just nice quality of life things for farming. So if you want to calculate the actual power consumption that you are going to use for the TCO, you can see I have a TCO calculator. And that's a spreadsheet that we've released. You can go take a look at. We've also put it on the chiacalculator.com/RY. But this TCO model basically allows you to put in the power of the farmers and harvesters. So this will include CPU, DRAM, boot drive, HBA. If this is a desktop, it's just the power of your desktop. If it's a Raspberry Pi, it's the power of the Pi. So it's just whatever you're using to actually use as the farmer. Now, the good thing is that farming doesn't take very much CPU utilization. So if you're building a dedicated farmer, you want to build something that has, very efficient CPUs that can go into these idle states on the CPU as well, because farming is only going to be about 1% CPU utilization, even on a modern CPU. So you generally don't need anything super fancy. And of course, you're going to need to have something to put the drives in. Now, if that's a JBOD, the power that is not the drives includes the expanders, the fans on the power supplies themselves, all the management stuff. So they consume just power for the supporting infrastructure. And the drives, I mentioned, if we're going to spend on a K equals 32, you're going to basically set the power idle at the idle A value for the drive model that you have, and the power active, just the random rate at 1%. So in general, you could make this easier and just, if you're trying to measure this yourself in your own spreadsheet, just the power consumption for all intents and purposes for Chia Farming is the power of idle A that the drive consumes. And networking, if you are using networking and you have a dedicated farm, like my equipment happens to be in a colo, and so I have a router and a switch and other things that are there, and I have to have them for Chia Farming so I can remotely access my farm, and those things contribute to the power consumption. And then your rack. So generally, this is if you're doing your own data center and people are doing high scale Chia farms in their garage, then you actually need to add dedicated cooling, and that kind of counts towards the power consumption of your farm. Now, generally the cooling is part of the non-IT equipment stuff. If you're calculating power usage effectiveness, you basically would calculate the total power consumed by the IT equipment, and then you're basically dividing that by you're taking the total power that is consumed in the data center, or total power you're putting in, divided by the power of the IT equipment, and that you get your power usage effectiveness. And so again, stuff like if you have this in a data center you're hosting yourself, the lights on the data center, the staff, the other cooling, all that stuff that is being used in the data center, that's part of this calculation. Okay, so now we have it. So now we have a good way to basically say, how do we sum up all the things? And it's very easy. So the way you do this is basically sum up the power of all these, and my TCO model does this automatically. And then you basically look at the total cost of the power, and you multiply it by your dollar per kilowatt hour, or your cents, I guess. And if you're in the States, it's like 14 cents is the average residential cost of electricity in the U.S. right now. You basically just multiply the power consumption over time, and you multiply that out by the kilowatt hours to get your total power consumption of kilowatt hours per month, and then you multiply it by the cost, and then you have your power consumption. Now, if you wanted to look at your power consumption metric, as a normalized metric per terabyte, you basically take the power of everything here besides maybe the cooling, because if you're calculating PUE separately, you don't include the cooling, but you include the farmer, the JBOD, the drives, and the networking, and you would basically sum all that up and then divide that by the amount of useful terabytes you have, and that's your watts per terabyte. And this is the ultimate metric for Chia farming, and quite, for TCO, all that really matters. You want that number to be as competitive as possible. So if you look at a desktop where you don't have a ton of overhead, you can kind of look. I've put the capex of total, which is the capex to buy the desktop and the drives and everything else, and then your opex, which is your power. This is over a 5-year TCO. You can see even in a 5-year TCO, the majority of costs in Chia are the cost of the drives themselves, which I think everybody understands. But you can see, 18 terabyte recertified versus used 8 terabyte, used 12. These are all pretty good TCO. Even 18 terabyte new is better than some of these other drives. So ideally, you want to have your TCO as low as possible, and that would mean you are as competitive as possible, which means you need to optimize your power for the supporting infrastructure. You need to be buying competitive drives, which again, you can see even an 8 terabyte drive can be pretty competitive, but that power, the OPEX per terabyte effective, is bigger than you're using 18 terabyte by quite a bit. So you have to get a better deal per terabyte on the drive and all the supporting infrastructure to basically make that equal out. Now on a rack scale, it looks a lot different, right? Because when you're trying to do and the example here I use with 18 terabyte disti is basically like $325 for an 18 terabyte drive, and using a 9.7 petabyte rack as an example, and that would include a couple servers to use as harvesters, and when you're doing this big scale, you actually need more equipment, and you can see you have opex, capex of the compute plus rack, which is basically all the other stuff that's not the drives, and then you have your opex of the compute plus rack, and then your opex of the storage. Capex of the storage is the green, that's the cost of the drives, and then your capex of compute plus rack, that's the cost of everything else. So you can see there isn't a one-size-fits-all model for Chia farming. Even in the enterprise space, if you get a very good deal on 8 terabyte drives or 12 terabyte drives, they can be competitive for Chia farming, even though they consume quite a bit more OPEX. Even in this example, I used nice new 90 bays for the 18 terabyte, and then kind of older 45 bays, for the use, which you're going to have basically double the amount of JBODs, but maybe they're take slightly less power than some of the new ones. You can see here though, if you got a 3 terabyte drive for, I think I put in $20 or something like that. So just, I don't know, maybe you can find them for $10. The amount of JBODs and slots you're going to need, the amount of power you're going to consume, it's a lot higher TCO than any of the other competitive uses. So, it's hard. When you have to look at this, even if you get an insane deal on storage for these small capacity drives, they are just ultimately not going to be competitive for Chia farming. 8 terabyte drives can be if you get them really dirt cheap. I to look at the model of what I put in here, but very, very dirt cheap. And if you're buying used drives, try to get the highest capacity possible, but also balance that with dollar per terabyte you're getting, and you can have a competitive TCO for Chia farming. So you can go to chiacalculator.com/ROI, and you'll actually see a copy of the model here. He used my model as the reference, which is the SNIA open source TCO model that I wrote for SNIA a long time ago. We've kind of modified that for Chia farming, and you can watch a video of me kind of going over the tool of how to use it. But if you just learned everything that you had in the video today, you'll be able to go in here and put in some values, and you'll be able to figure out your TCO for Chia farming. And again, TCO for Chia farming, the power consumption is a big piece of that for the OPEX. But again, if you're doing Chia right, then one, the capex of the cost of the drive will be the majority of cost for your TCO, and then your OPEX will be really competitive if you're using high capacity drives and you have a very efficient setup. Then your watts per terabyte will be as close to as possible to the watts per terabyte of the drive. And so again, the theoretical maximum watts per terabyte of the drive, can't effectively be better than what the drive itself supports. So again, take a look at this, play with the model. It's really exciting, and we will circle back with any follow-ups. So thanks, guys.